Okay, maybe we'll get started. People are still coming in, but so it's a great pleasure today to have Peter DUEBEN from ECMWF, the European Center for Medium Weather Forecasts. For those of you who actually don't know it. So Peter actually got his PhD and was working at the time at Max Planck in Hamburg, doing very much work on numerical modeling of the atmosphere and ocean. And then he moved on to do a postdoc at Oxford with Tim Palmer, who was at the time also at ECMWF before that, working very much on the modeling of the atmosphere and very much on chaos and predictability of the weather system. And then after that, he actually moved to ECMWF and has become, since over the last couple of years, the head of the Earth system modeling section. And I'd like to emphasize that ECMWF has really been visionary in terms of the use of AI. They could actually have really been very careful, and they really embraced that even at a time when it was just emerging at the team a couple of years back, and that really led to the transformation that we are seeing now at ECMWF, and they are very much the leader in that space. At the weather forecasting, in the weather forecasting context. So it's a great pleasure to have Peter today, and very much looking forward to hearing what are the next thoughts in terms of the use of generative AI and generative machine learning for Earth system modeling. Thanks so much, Peter.
Thanks a lot for the introduction and also for the invitation itself. It's fun to be here. It's kind of difficult to make talks like overview talks these days because you never really know whether you still need to convince the audience of machine learning or whether you kind of need to kind of caution the audience regarding machine learning. But I'll try my best, and you can interrupt me if you want and say like, Peter, we know all this, so go forward, please. So we're going to talk about how generative machine learning will change how we do Earth system modeling. I'll start with a what first, like what do we actually do in our system modeling right now, in particular with machine learning. As Pierre mentioned, I'm coming from this institute with a strange acronym, ECMWF, and what we basically do here is that we build global weather prediction systems, and we're kind of looking into the medium range, so a couple of days ahead, but we also have seasonal predictions. But in general, we try to basically build models that kind of encapsulate what's happening in the Earth system to do then weather prediction. And as you probably know, we have been quite good in doing this as a community. So I like to start the talks actually with videos like this that is showing you simulations for physical models. And this is basically a simulation from a kilometer scale model. So it's global and it has a grid spacing of, I think, 4 kilometers. And what you see is basically all model data. And you see how kind of realistic these models are these days. So it's kind of quite amazing how far we actually got developing those physical models. They have something like 1 million lines of code. They're running on supercomputers. They kind of encapsulate the Earth system in the sense that you have all sorts of Earth system components. And they also act as digital twins in the sense that, as you can see here, basically, you cannot just represent what you see but in observations, but you can also kind of look into 3D fields and basically look into all of the different details and kind of play around with the data and also play around with the model itself. So physical modeling made quite good progress over the last couple of decades. And this is the slide that ECMWF employees typically show to kind of represent this. So that's what we basically call the quiet revolution. And the plot on the left is showing you the time on the x-axis in kind of years over the last couple of decades. And on the y-axis, you have basically forecast accuracy as the anomaly correlation of geopotential height at 500 hectopascal. If you don't know what it is, no problem. Basically, it's an indicator of like how good a weather forecast quality was for prediction. And the different colors now are different forecast lead times. So you see very good predictions, very high quality for blue, which is 3 days, less so for 5-day weather forecast, and then 7-day forecast and 10-day forecast. And you see that those lines are going up. And roughly those lines are going up with kind of basically the slope of something like 1 forecast day per decade. So if you wait for 20 years, you will have a forecast that is 2 days better in a sense that a 5-day prediction is kind of as good as a 3-day prediction has been 20 years ago. So that was a quiet revolution, and that basically happened by improvements of our observations, improvements of the models themselves, improvements of high-performance computing, and also the knowledge how to build those models in principle. But it has to some extent slowed down. So if we kind of now look into the last 20 years, we actually haven't really seen that kind of 1 day over decade timescale anymore. And it seems that it became a little bit more tricky to actually kind of build those physical models, even though they are kind of improving in the quality of the individual like fields and realism. So at ECMWF, we're developing our physical model, and we have lots of things that should be done and is done at the moment. So we have lots of ways of actually how to push forward our physical model in principle. I'm not going to go into detail, but believe me, there are very smart people looking into the development of the physical model. So it's by no means stopped. But if you just think about the quality of forecast scores, many of those developments are actually not going to lead to sudden jumps in forecast quality. So it's probably fair to say that this quiet revolution has slowed down a little bit. Why is this? There's several reasons. One of them is actually that it is more and more complicated to make the best use of modern supercomputers for physical models. So you all know about GPUs and how they have changed the world of high performance computing. It is a nightmare to port those 1 million lines of code models to GPUs, and it has been a nightmare for the last 10 years, and it still is. So it's still very difficult to actually kind of make efficient use of this hardware. And at the same time, Moore's law has also slowed down. Moore's law means that you have an exponential increase in compute power over time. And we have had this in the past. So again, on the bottom right, you see a figure that is showing you the time in decades on the x-axis, and on the y-axis now is actually computational performance. And the different columns here are the different supercomputers that we worked with at ECMWF. And you will see that there's basically like a linear trend of kind of compute power going up in the graph, but it's a logarithmic graph, so it's an exponential law. And that's basically Moore's law in principle. And this actually lets us to be able to also increase spatial resolution, which is indicated here with the dashed line for the ensemble and the continuous line for the deterministic model. And if you now continue this line to the end, you will see that we're expecting something like a factor of 100 in HPC improvements until 2030. And if I'm honest, I think I would be very happy if we get a factor of 2. So the high performance computing increase has really slowed down, which has an impact on the physical modeling in that sense. And while we actually can make now kilometer scale models viable also for like longer term and simulations in climate, like decade-long simulations, and also numerical weather predictions, and we can actually see improvements of the models for a lot of different kind of local features, it's very hard to actually see very kind of good improvements of the global scores, and that's what you see in the slowing down of the quiet revolution. There's also the component of observations and data simulation, and I'm not going to comment much on it here, but I think it's also fair to say that we don't really expect any jumps coming from that either for the physical modeling side. And at the same time, you have the machine learning revolution happening. So you have basically this jump here. So it's again a similar plot that we had before, just starting in 2006. And you have now a jump here that is basically happening from the physical modeling quality to the machine learning quality. So the dashed line on top is the machine learning quality. And this basically means that the quiet revolution, as we have known it for decades, is stopping, and the machine learning revolution is starting or happening right now. The machine learning models are years ahead in terms of physical forecast scores compared to the physical models, and also you can trust those models. So it's really that the machine learning models are also not just producing something that is unphysical and very difficult to actually believe in, but you can actually kind of also get trustworthy predictions on the medium range timescales. And at the same time, you can still get score improvements for the physical modeling, but only if you think about hybrid machine learning approaches, for example, nudging, where you kind of nudge the large scale to the machine learning model. But in principle, you have this step change right now in quality. And that's hitting the community quite hard in a sense that obviously a lot of people are kind of realizing this now, and that machine learning is going to be probably the future for a lot of forecasts. And at ECMWF, we basically have embraced this fairly early on. And nowadays, we actually have a deterministic AIFS system. So AIFS is our machine learning brother of the IFS, the integrated forecasting, the physical model. And we have it now running operationally for the deterministic model. We also have it running operationally for the ensemble model. We have a library that we developed together with our member states. It's called Anemoy. It's basically a basis of model development for NWP, both for limited area models at the member states and global models with us. We're also looking into hybrid modeling. So in particular, nudging has been extremely successful. So you take the physical model and you nudge the large scale to the machine learning model, but still run the physical model in the background or in the foreground, whatever you want to say there. And you basically kind of get a lot of the best of both worlds to some extent, getting the large scale scores right, but also the local features from the physical model. And there are also other approaches like AI DOP, where we basically produce predictions directly from observations. So we don't really use the reanalysis anymore for training. And these approaches are getting more and more interesting and more competitive. So we'll see where we land with these approaches. And then also as part of Destination Earth, we're building kind of Earth system complexity models as well, where we also add land, wave, ocean, and so on and so forth to the model components. So it's busy days. We're doing a lot, basically, also to operationalize those ideas. And often it's kind of phrased that it's very difficult to actually see where this route is, like where machine learning models are going in the future. So what are we actually doing in the next 5 years with machine learning? And to some extent, I don't really think that's so difficult to see. I think in the end, machine learning is a supervised learning task in most of those approaches. And the question, like you do input-output mapping, and you kind of have a sophisticated mapping procedure, but to some extent, we have explored that quite well now. And we also know that we can learn everything that's in the data, at least in theory, because we know we can just assume basically that machine learning can extract information that is there. And then a lot of the questions are becoming fairly easy. Like, do we have the right software to do the developments? Yes, we do. Do we have the right algorithms to do the developments? We can almost certainly still improve them, but in principle, yes, we have them. Do we have enough compute? Not at home, meaning not in the weather centers normally, but certainly at kind of public machines and larger machines. That's definitely true for Europe with EuroHPC, but probably also for the US. And I think there are basically two fundamental questions that we still have to answer. And they are basically the two questions that really will change how we kind of build those models and what we do with them. One of them is, how many models do we actually need? So how big will the models be that we develop? And the other one is, do we have enough data? Let's focus on the first question for now. How many models do we need? I think it's fair to say that the gene pool of models in deep learning, like for deep learning weather models, is actually kind of not very big. It used to be that there were like new developments every month and everyone was switching to diffusion models and whatnot. But I think we have converged in a sense that there are not too many new developments happening right now on the supervised learning front. So the gene pool actually has decreased and not increased. In the representation of individual model components is quite essential in principle. If you want to build an Earth system model, you will also need domain expertise to do this. So you will actually kind of need a team of people that is not just software engineers, but also domain scientists by now. And this basically makes the whole thing quite complex. So if you now build an Earth system model, you actually need a complex set of people again. So the physical model is extremely complex. The machine learning model used to be small, and now we're kind of increasing complexity here. And also, like the unified model of an Earth system is probably better in the long term than many task-specific models. In particular, if we think about trust, we want to trust those models, and we can trust a model more easily if it's representing all the different model components correctly and not just the one thing that we're actually focusing on. Seamlessness still seems to be useful. So we learn from seasonal prediction to daily prediction, and from daily prediction to seasonal prediction. So that's still something where we learn from it, maybe not just in terms of exactly the same model, but definitely in terms of the architecture and kind of the assumption of training data and so on. The models become more and more complex. So I think we are at 200 million degrees of freedoms right now with AIFS ensemble, and the number is still probably growing exponentially. And my prediction is to some extent that we will have a very small number of those big models, basically, and that these models will be used a lot by the wider community, basically. So it's not going to be that every PhD student will have their own weather model. I think it's more likely that we will have big centers developing very complex models, and then every PhD student will run those models, maybe even just on a single GPU. But in principle, I think these tools will be fairly centralized. But model doesn't really need to be the one forecast model for day 3 forecast. It can actually be a latent space representation that is then retrained or kind of with tail networks kind of refined or whatever people are working with basically. And this is kind of coming or leading me towards what we call a foundation model, right? Basically, if we assume that we have big models and you want to have models that are quite generic, and we're building what we call a foundation model in the project that is called Weather Generator that I'm coordinating. And here we basically want to build a big predictive model system that can take all sorts of different data as input. It could be reanalysis data, it can be simulation data, it can be observations. And then it will also produce all sorts of different output data sets. So it can be predictions on different time scales and spatial scales. It can be data simulation tasks. It can be energy output if you, for example, bring your own energy farm data to the mix and stuff like this. So it can be kind of used quite generically. And the ambition really is that it should basically be able to use all those inputs. Basically, whatever data you have available, you can give the model. And then it can produce either global or local predictions, and it can produce 100-meter resolution locally or 100-kilometer resolution globally. It should be possible to work with this in the past, the present, and the future. It will also be based on self-supervised learning, so mass token approach, basically, to make it more learning, a kind of a more generic and more objective latent space. And then it should also scale. So it also should really kind of be a very large model with a very kind of refined latent space in principle. And to some extent, that's still a little bit of a dream. So that's what we want to do. And we also don't really know exactly how far this will bring us. But once we have built such a model, it should be very generic. So you have the weather generator with a very large latent space. And then you kind of bring whatever you have as data. So if you kind of give it satellite observations or synoptic observations inputs, and you kind of make an output towards the reanalysis product, you have a data simulation tool. If you bring it IFS, like physical model analysis, initial conditions, and you kind of run it into the future and you let it predict things, you have a global weather forecast, and so on and so forth. So you can really pick the application you want. And it can go so far that you actually kind of just produce, for example, a date. So you can actually ask the model to generate like sort of realistic weather patterns for 2020 and 2030 or something like this. And the model should kind of deliver something like this. So very much following also kind of the path that C-Bottle from NVIDIA is kind of looking into of more like generic applications. So that tool should be very generic. And it's kind of the ambition that this is kind of really the one weather generator model that we develop in the project. And we have like 15 partners working on it for 4 years. And we already have like 22 application areas that we're looking into this project. However, I'm absolutely happy to admit that this is a bit of a gamble. So it could well be that an AIFS simulation with 200 million degrees of freedoms is going to be better in medium range weather predictions in the future. So there's no guarantee that this is actually going to be a useful approach in the end. So it's a bit like, well, it's something that needs to be explored, and Weather Generator has a critical mass to do this on that scale, but by no means it's guaranteed that this is going to be the best model in the future. We'll see. Just to kind of show you that it's actually working. So this is kind of where we are at the moment. So we can already kind of put in a lot of different data sets and also get useful data out. So it's not just a dream anymore. We kind of are well into the developments right now, but there's still room for improvements and we're still working very hard on the different details. Okay, next question. Do we have enough data? And this is probably a very controversial slide, so I'm sorry about that. But I mean, there are different applications that people are looking into with machine learning. And for some of them, we have enough data, and for others, we don't. For parameterization emulation, for example, I would say we have enough data if we just work on model data, but just emulating model components is a bit pointless if you just train from model data. So actually, if you want to really be better and do something useful with parameterization emulation, you should probably go towards observations. And that's kind of very tricky and very hard to do. So, and then again, the question is actually whether you have enough data. Global medium range weather predictions. We know that AIFS is producing better scores than IFS. So yes, we have enough data. The question is, what is kind of the physical limit? What is the butterfly limit? So there's kind of like interesting literature coming up on that question, basically how far can you go? But in principle, yes, you can build competitive models with what we have. Seasonal predictions. It's a tough question, actually. It seems to be the case that machine learning models are really interesting and nice, but I think it's not it hasn't been decided yet whether seasonal models for machine learning will be better than, for example, a physical model with post-processing. So there's still a lot going on, and also it depends a little bit on what you're interested in. So there's also an indication that ERA 5, for example, may not be enough data in terms of different weather situations to actually kind of learn all relevant teleconnections that you have on seasonal scale. So it's an interesting question to be looked into. Global data assimilation in terms of like AI approach, you just take observations as input and kind of make predictions. It's also still up in the air. I think that's going to be extremely interesting to kind of follow that this year and next year, what the developments are, but still to be seen, I guess. For the ocean, it's clear. For the surface, we have a lot of data. For the deep ocean, we won't have ever enough data to kind of really train like numerical, like a machine learned ocean model for the three-dimensional ocean that is not based on physical model data. So again, probably a gap here. Land modeling, I presented this before and said, yes, we have enough data. And then Pierre mentioned, no, we don't have enough data. And he's right. So we have enough data again for the surface. But if you think about like, we should definitely have more observations, in particular, if you kind of go to deeper layers of the into the ground, you really don't have enough data. So it depends on, again, like what you want to actually emulate or simulate. CS modeling, probably yes. Problems with volume and height, but coverage is definitely enough data there. Global atmospheric chemistry, we have a lot of data. The problem is that this data is often of poor quality, so you probably need more observations and better data sets, and then probably, again, fill it in with physical models. Climate simulations and climate sensitivity, I would say no. Others would disagree and say maybe yes, but I would definitely say it's going to be very tough to really believe those models in climate sensitivity, also for tipping points. Extremes in climate model simulations, you can probably kind of fill in physical model information and then you can generate enough data sets. Local downscaling, again, questionable what data you actually have on the ground that you can use, but very interesting for 2-meter temperature, probably also for precipitation. But again, you may actually want to kind of cross-check with kilometer scale model it. And then gray swans events, you probably know the paper of tropical cyclones by the group in Chicago. So you probably have enough data if you use the physical models as well. So what do you do if you don't have enough data? You actually kind of go back to the physical models or observations, depending on what you have. And for the physical models, this basically means that you again want not just any odd physical model. You actually want to have the best physical model that's that's available. So kind of working on those physical models and extending those in particular to kilometer scale is still something very useful. So even though we are in the middle of the machine learning revolution for NWP, it doesn't mean that we should stop physical modeling. We actually still need those models to generate training data sets. And the physical models, though, should kind of change a little bit of what they're doing in a sense that they should actually more think about what gaps can they fill in the data sets rather than just kind of forecast scores. And they should also think about like how they can make these data sets available for machine learning modelers. And for observations, it's also like, I think new questions should be asked, like what data sets do we actually need to fill the gaps? For example, land surface modeling, deeper layers of Earth and stuff. We don't have a lot of data, and we need enough data to actually generalize with machine learning models. So that's something that we should close as a gap. But the title of my talk was actually on the how and not on the what. So far I've talked a lot about the what we're doing and what models we are developing. But I think the really interesting question right now is actually on the how. So how do physical modelers or machine learning models develop those models? Because I think that we will see an extremely significant shift in how people are working in modeling centers like ECMWF. The first point is programming with large language models. So that's if you are following, I don't know, X or LinkedIn or something like this, you're probably kind of sick and tired of all those comments of like how vibe coding is going to change everything and how vibe coding is going to change nothing and stuff like this. But I'm actually convinced by now that this is going to have a significant impact on how we build models. So I don't know whether you've tried out your favorite LLM in the past kind of couple of weeks or month, but they are extremely powerful by now. And software engineering will change. Maybe not quite 10 times as I've written down here to provoke you a little bit, but I think it's very much likely that a software engineer will use those tools on an hourly basis. And this basically means that productivity will shoot off. And this is, again, nowadays fairly reliable and not just producing bugs that you then need to debug. This is changing how we build models. So coded languages are becoming fairly irrelevant in that sense. And also, it's kind of much more important whether a code like IFS is, for example, low level or high level, rather than whether it's written in Fortran or Python. So because you can do these changes quickly with LLMs. Also for model portability, it's like all the efforts that went into GPU coding in the last 10 years can probably be redone very, very quickly with a powerful LLM today. So a lot of this kind of really hard work is probably going to be solved by very soon. And this basically means that you need to focus on different things. And for a physical model, this means that you need to modularize your code, that you actually kind of can feed those modules to an LLM. You also need to kind of reduce the size to kind of make it more easy to handleable. You also need to think about CI testing, like continuous integration testing, to actually kind of identify whether there are any bugs that you have produced with coding. And then also you need to think about how you actually perform, like link those different model components to each other with an API. So that's changing quite a lot. Also, as a community in IFS, for example, we're hardly using any external libraries. So we're kind of using BLAS and LAPACK and stuff like this, but we don't really use a lot of external libraries. In a code like AIFS, we're using loads of external libraries, starting from PyTorch, basically. So there's a shift again happening, and this basically is going to be also very influential of how we kind of develop model codes and also what kind of codes we're developing. Because as modeling centers, we should really focus on those parts where we are world leading rather than kind of build nice and interesting libraries. And this would basically allow the modeling centers to kind of keep their development teams small and focused, which then again improve productivity. Third point, data compression. That's a topic that has been discussed for a long time now, but I think nowadays with kind of also like data volumes exploding, basically we need to do more with this. And actually, there are a lot of low-hanging fruits that we haven't really kind of touched as a community. So I think it's very much possible to reduce the data sizes we're working with kind of lossy compression techniques and produce like a factor of 10 compression rates. There are good examples in the past, and we just need to kind of learn how to trust those methods, basically. And once you've done this, you basically have, you're going from memory to cache in terms of speed, from disk to memory, or from tape to disk in terms of cost and speed with a kind of reduction of factor 10. And this, again, is going to boost your productivity quite a lot. Number 4 is observational data sets. So nowadays, it's extremely difficult still to kind of work with more than 2 or 3 operational data sets at the same time, because they are normally stored in different formats, they're available on different clouds, and blah, blah, blah. It's a lot of work, basically. But a lot of efforts are happening right now at ECMWF, at EUMETSAT, at EUMETNet, at Weather Generator, and others to kind of basically bring those data sets together. And since we don't really have too many of them, I mean, let's say we have 100 relevant observational data sets for like global weather predictions, for example, this problem will be solved at some point. So these model data sets, the observational data sets will be approachable and usable for the open community, basically kind of storable probably in 1 petabyte of data. And also really easily accessible by everyone because those library tools are going to be there. And this means that the community will have much more better ways of actually kind of comparing their results against observations and kind of to spend much less effort there, basically. This brings me to number 5, which is that once you have all those observational data sets and model data sets easy to use, it's going to be much more easy to kind of verify your model quality that you have. And that's fantastic again, because it basically brings down developing cycles of the model development significantly. And also it will democratize kind of the access as well, in the sense that not just ECMWF can build top models because they have all the data, but actually everyone can kind of build top models because they have access to data and can also compare themselves to other models. The downside is that it will naturally lead into an overfitting challenge. So naturally, we will probably kind of find a lot of people overfitting their models for the data set that is available, which are huge data sets in the end, but still it will be difficult to kind of, test physical reliability then. Number 6, interactive access to HPC in large data sets. So nowadays, you can actually run a 20-kilometer physical global model on a single compute node, and you will soon be able to run a 4-kilometer machine learning model on a single compute node. And once it's happening, it's kind of much more easy to kind of really do interactive use cases for your application. So we will have much more development of interactive nodes, sorry, and do verification in the browser, for example. And this also means that you can combine it like with kind of fly-through visualization and stuff like this. So it will be much simpler or much kind of more much easier to actually kind of really follow the physical developments of like how clouds are propagating and convections happening and stuff like this in real-time simulations of your model. And then generative machine learning. And I think this actually may have the biggest effect in principle. So if you have a tool like weather generator, you can probably, you can generate whatever data set and observations you want to produce in the past and the future, for example. And you can also generate weather situations, like, I mean, like, as I said, following the sea bottle approach, like you want to have tropical cyclones in the Caribbean in 2030, you just ask the tool to do it, and it will generate you weather patterns there. And they will be kind of fairly sophisticated and interesting to play around with. Then you combine this with visualization as well, and then you do teaching, for example, and you will basically ask your meteorology class to just generate a tropical cyclone and then change the sea surface temperature and see how the tropical cyclones will basically change and what they will do and stuff. And this will not only be able to kind of really change how we look into physical processes and how we do training and teaching, but also how we evaluate models in a probabilistic way. So I think there's going to be a lot of change of what's going to happen in principle of like how we deal with these models. And if you just take one of those 7 points in isolation, I think that's kind of not going to be a big of a change. But if you take all of those 7 points in combination, and then you kind of look at the timescales as how fast we are developing in that space, I think we will have a significant shift. And it's very difficult actually kind of to really suggest to PhD students and master students these days, like what they should actually focus on in their education, because we will work very differently in 5 or 10 years from now. The future of physical models, it's basically, the problem is really that we nowadays see that machine learning is hitting the ground. And this basically means that a lot of the developments are kind of diverted from physical models to machine learning models. And to make it even worse, it's also going to be very hard to actually kind of find good developers of physical models in the future and to kind of find the right compilers, hardware, and stuff. So I think we really have to trust our efficiency increases with the work with LLMs, for example. But even then, it's going to be difficult to find the convection expert, for example, focusing on the physical modeling rather than the machine learning models. So we will have problem here. The resources will reduce, and we will need to kind of be able to kind of maintain what we have in terms of quality rather than develop new and much more fancier models in principle. A lot of the models will not survive the next 10 years because they will be replaced by machine learning models. So it will be centralized as well. And as a physical model, we have a couple of things that we really want to do. I'm not going to go into detail, but I think we should really focus on like configurations that are sustainable over time at a reduced level of staffing and resourcing. And I think that's not easy to do. You can do it in principle. You can do future-proof models that kind of follow also the ideas of LLM coding and blah, blah, blah. So you can, for example, build models based on domain-specific languages like GT4Pi and so on. So it's not that we can't do that, but I think the problem really is that these models are so complex and also the workflows are so complex running either for like CMAP type simulations or weather type simulations, that kind of just the development of the model is not enough. You also need to kind of implement them into like an operational system. And then again, you need a lot of resources, and that's typically happening on the time of like decades rather than years, but we don't have decades anymore. So we kind of really need to think about like, where do we want to be with a physical model in 5 years from now, and really think about how to get the resources and the critical mass of people there. Machine learning models, a lot will be happening via general open source infrastructure. I mean, you have probably heard about Anemoy before. You've probably seen people working with it. There's also like GraphCast and neural GCMs as models that are kind of happily used by the community, infrastructure that was developed somewhere and is now open source and people can use it. There will be more of this also regarding data sets and so on and so forth. In general, if you think about how the efforts will develop in machine learning, I think the data handling, as I said before, is going to go down in the sense that it will be much easier at some point, and you can only add so much observational data sets to your list. The data set generation is going to go up for physical modeling and kind of to think about like how to close the gaps. Architecture development seems to be getting fairly boring these days, but some people on the call may disagree with me. So I'm happy to kind of receive the feedback that I'm wrong after the talk. And then HPC efficiency is something that we really work on right now, and we need to kind of do a little bit more. But again, at some point, problems are going to be solved. So it's going to be a bit more boring there as well. The future Earth system model is in principle from the Earth, like ECMWF point of view, not saying that I'm speaking for ECMWF, but like if you are a forecast center, you actually need to think about like how are you kind of delivering predictions in the future. And I think that this is going to kind of change quite drastically again. So you're going to have high resolution physical models and you're going to have observations. These are basically going to kind of develop infrastructure and data sets that can be used. The data infrastructure will be kind of linked to all the kind of the software tools that are out for the community, like pre-trained AIFS models or weather generator models and libraries like Anemoy, where you can kind of train your own model with it. You have visualization tools and kind of basically a lot of capability to also look into the data. You have operational products as well. Obviously, this will change a lot towards machine learning, coming from basically only physical modeling in the past. We will basically see a lot of machine learning there. And then you have user who basically are more independent in the sense that they bring their own data, which is important. And then they use the infrastructure and also the operational data sets, and they run basically their own tools. And they will have fantastic tools. So it will be possible to make like infinite resolution prediction at a specific point at a very high quality for weather. It kind of whatever we can extract from climate simulations for climate. And they will also kind of have much better tools to actually look into like what they produced in terms of visualization and these kind of things. Even think about virtual reality, I think very much on the radar of what can happen in the future. And basically, in the end, this means that the differences between physical modeling and machine learning models will really blur in a sense that it's going to be, the models are going to be based on data sets that kind of come from physical models and observations, but then are kind of combined with the machine learning model that are then retrained for training networks for applications and blah, blah, blah. So it will be very difficult to actually understand really where a signal is coming from in a sense from the original data set and so on. And also, it's going to be much easier for new user groups to actually kind of engage. So there will be more more people who can actually kind of make use of the model infrastructure. So Earth system model itself, it's coming from a world where the big holy grail of Earth system modeling was to kind of build a holistic physical model that is good in all aspects, and kind of if you improve all aspects, you're going to kind of get a better model overall. And this is not changing into a concept where you basically generate physical data, like data sets from physical models and observations. And once you have this, you actually use machine learning to really extract information and make it useful in numerical weather predictions, or also for climate simulations, I guess, as kind of emulators. And it's also much less interesting to kind of just look into time series from the 80s, from the 1900s to the 2100s. It's much more interesting to also kind of explore this on a snapshot basis, for example, or just looking into like a weather forecast of a specific weather scenario, for example. And you can initialize those models basically everywhere if they're kind of built in a decent latent space, and they can be used then. So it's also different in a sense that you kind of don't look so much on a like 100-year data set or a model simulation anymore, but you rather think about like a holistic foundation model that has learned all the kind of connections in the data sets, and then you just explore how it's kind of generating data. That's fantastic, but it's also very dangerous because it will be very easy to create a machine learning weather forecast data and information extraction from those kind of very large models. It will be very difficult to actually kind of understand whether it's kind of based on real physical information from data sets. So it will be very difficult to actually justify that the signal that you're seeing is not just hallucination, but actually kind of based on the training data information from the beginning. And that will keep us really busy, in particular for climate modeling. So everyone will build machine learning models and produce very high resolution, beautiful pictures, but it will be very difficult to actually understand when we are wrong. And for weather simulation, that's not such a big problem because we have seen and built trust with tools like AIFS and GraphCast. They don't really produce very stupid results that are totally unrealistic. And we can also empirically show that that's the case by looking into hindcasts. But for climate, it's going to be quite a nightmare. So I haven't really seen a model that was really just basically a machine learning model that was producing like climate scenarios, if you want, without looking into some sort of physical modeling output in a very reliable way. I know that there are kind of some groups looking into this, and Dale Run would, for example, probably disagree with me, and that's fantastic. Please go ahead. But at the moment, I don't really see kind of any kind of machine learning approach that wouldn't kind of trust physical models, for example, for looking into 2100. So I think the number one evidence, as the number one priority of scientists in that field, should also be kind of to think about how to actually make sure that what you see in the climate modeling is reliable and not just hallucination, because this is going to be really the killer argument against all machine learning climate simulations in the future, and the part where it's really going to get very tricky to actually identify what is a real physical or scientific information that comes from the data sets and what is actually kind of just invented. And this basically means that you really need to be quite critical in those simulations and kind of really kind of try to think about way of challenging some of the results that will be shown. And I think I will leave it here. I talked for 40 minutes. I think that's probably within the time scale that I was asked for. And thank you for your attention. And I would be happy to answer any questions.
Thank you, Peter, so much. That was a great presentation. If there's anyone who has a question, you can feel free to unmute yourself and ask. Dion, I see that you put something in the chat, but please feel welcome to unmute yourself and ask your question.
Hi, Pierre. Thank you for the talk. I just wanted to ask, I mean, these are some very cool results. And I've heard before that for weather forecast, ML has been working amazingly, as well as I think the best physical models you have. But I'm just wondering, like, to what extent do you think that this can generalize to climate modeling? I think a bit of the argument I hear is that weather forecast, you assume that the weather days from now is follow similar patterns to the weather today, and so it's an in-sample problem. But climate change, by definition, that is an out-of-sample problem. The climate is changing and we don't really know the dynamics of it. And actually, that's what we are trying to predict. Then that makes things more difficult.
That's a very, very tricky question, right? Because whatever I say, I'm going to be wrong, I guess. But I mean, in principle, GraphCast came out Christmas 2022, and all the domain scientists in physical modeling were saying like, yeah, that's pretty nice, but the models are not going to kind of be able to get extremes right? And they had a point in the sense that it wasn't kind of clear that they would get extremes right. But now we have 2026 by now, and we basically have seen, and over the last couple of years, that these models are actually very good in extremes, in a sense that if you look into weather forecast busts for the physical model and the machine learning model, like bust defining basically, or the model was very wrong and in a specific weather situation, and the ensemble was also very wrong, it wasn't really representing the ensemble spread rightly, for example, then actually the AIFS has less forecast bust than the IFS. So I'm sure there could potentially be a tropical cyclone that would not be as intense in the AIFS as the IFS, for example, which is obviously a big thing, but I don't think it will happen very frequently. And most of the time we can actually trust those models. So empirically, we actually have learned to trust those models. And that's what I'm saying, basically. And for climate, it may be that those models will be able to generalize well, but can we ever trust these models for prediction in like 80 years from now? I'm not sure, right? I think there's kind of the fundamental problem there, that even if the model could be trustworthy, we wouldn't know. Is it kind of an answer to your question? I'm not quite sure.
I guess maybe a sub-question to that is, I'm wondering, I mean, you speak about empirical evidence for how trustworthy a model is, right? But that's often sort of a hindsight kind of thing, especially if you're doing like century-long forecasts, I guess. I'm just wondering, like, is there some other way, do you think, to really assess whether a model truly understands tropical cyclones or weather?
Yeah, I mean, you can try to just kind of to understand what the model is doing, and there's kind of fantastic work happening in explainable AI and stuff like this. But I think in the end of the day, it's going to be difficult. So I think in the end of the day, you have to trust, well, you have to collect the evidence. And I really don't know how to do this for climate. I mean, that was kind of one of I think if you want to take away one message from my talk, I think it is that it will be very tricky to kind of really identify whether machine learning model for climate is actually producing something very useful, and that this is a scientific challenge that we really need to kind of think about as a community. I'm not that confident that we will actually solve that problem, but I think we should really think about ways of doing this. And I don't really see much happening in that space. I mean, people building phenomenal, great machine learning climate models, but I don't really see the kind of the approaches that actually make that really like trustworthy.
Yeah, thank you. And it is pretty amazing what these models have done for weather forecast. So that's amazing in and of itself. Thank you.
Absolutely, yeah.
Okay, let me see. Here's a question in the chat. Peter, how do you see hybrid methods coming in to integrate with physical ESMs in the next years and decades?
That's a fantastic question. We're seeing a lot of different hybrid approaches, and I don't think we have we really know what the best hybrid approach is, right? For example, neural GCM is trying to kind of combine a dynamical core that is physical with the kind of the physical parameterization, or the field kind of changes in the parameterization basically that come from machine learning, and they're getting good results. And at the other hand, nudging is doing exactly the opposite by kind of fixing the large scale features and taking the small scale features, so like more the physical parameterization, really again from the physical model. So I think it's up in the open what's going to be the best approach. We're significantly thinking about nudging also for operational use. I'm not saying we were going to definitely do this, but it's something that we are really looking into. And I think the way how to define a physical model in the future is going to be very difficult as well. So typically we kind of compare our forecast with kind of the predictions of other forecast centers, and that's used to be kind of easy, but I think in the future it will be more difficult because you will actually need to understand how much machine learning and where is machine learning used to kind of really have a level playing field to some extent. So I think there will be a lot happening on that space, in particular also with approaches like nudging.
What is so what has been ECMWF's experience with physical constraints on ML training, and how might that tie into or how might tie into climate modeling? How it might be different at the climate scales where you have less data to work with?
Yeah, I think we are, as everyone, we're playing around with these things, right? And I mean, there are kind of some obvious things like, okay, we shouldn't have negative precipitation. So yes, we can make sure the model doesn't have negative precipitation. And then there are kind of more tricky things like, I mean, energy conservation and stuff like this. And I mean, I think that's really, there's a lot happening in the literature right now. And we are kind of looking into this a little bit. I think we have been on the slow side with this in principle. But again, it's going to be interesting. I think we have to be a bit careful that we don't over-engineer the constraints. I think that's not an ECMWF view, but my personal view. I think we need to be a bit careful that we don't kind of make sure that this kind of one loss function is kind of like weighted by 0.3 and the other loss function is weighted by 0.8, and then you kind of do a lot of like hyperparameter tuning that then again will lead to overfitting. So you can you can have all sorts of constraints, and you need to be careful not to overdo this, but in particular areas it's very effective. Yeah, so that's not a good answer to your question, DG, but basically the answer is we're looking into this, and I think that's really like an open book. There's a lot to be done.
Thanks, really interesting. I'm wondering, once the kind of ML models basically become universal function approximators for our like current reanalysis products, do you kind of see future progress being driven by kind of like replacing or adding like observations directly into the training versus like improving the reanalysis via improved physical models? Or
very good question. So I'm leading the US system modeling section at ECMWF. So naturally, I obviously think that we still need a model, right? And that observations to observation is not going to help much and stuff. But there's another person, Tony McNally, who's leading the assimilation section, and he naturally thinks that kind of you can basically do observations to observations training with AIDOP, for example. And once you've done this, you can also think about reanalysis products. And I think the jury is still open there. I think we don't really know exactly. I mean, we see that the observations to observation approaches, like doing data simulation with machine learning, are getting better and better at a very impressive speed. And I don't know exactly where they will land in a sense, like whether they will be kind of just better ever than kind of having the kind of more conventional reanalysis data sets. So I think that's still an open question. Once that's done, like if they show this, and this could well be happening within this year, right? I mean, there's a lot of development going on. Then you can actually ask the questions like, do we need a physical model? And what is actually then the model? Is it the latent space? Or so then a lot of other questions coming up that are really interesting. So I think that's again, I don't think I will really answer your question saying this, but I think it is very open how far we can go there. And that's probably one of the very interesting questions to be solved this year.
I can jump in. Hey, Peter. Yeah, I mean, I think in terms of the trustworthiness for climate modeling, apologies if there's a baby screaming in the background, is that, I mean, it's not a unique issue to machine learning, climate models. Of course, a lot of the same issues exist for numerical and physics-based climate models, including overfitting on historical record. And so, I guess one approach that people are thinking about is using paleoclimate as a sample test case where we at least have some data from for validating physical climate models. Do you think this is a good approach for machine learning climate models as well?
Yes, absolutely. So, I mean, first point well taken. So I would have given a similar talk 5 years ago and would have said, like, can we actually answer questions like climate sensitivity with a physical model, because we are overfitting as well in parameter optimizing them towards this. So point well taken. Physical model is also not the silver bullet in a sense that it's also questionable whether they can answer those questions. Otherwise, yes, absolutely. I mean, you have a fantastic climate model, right, yourself? So a machine learned climate model. And I think you're looking into a lot of questions about energy conservation and stuff like this, and you do it in the right way. And I think your question was like whether you should look into very different climate zones, right? Prehistoric and stuff. And I think, yes, I mean, that these are methods to build trust. Like, how does a machine learning model, like, what do you need to actually make a machine learning model work on Mars? What do you need to make a machine learning model work on like 1 million years ago based on climate records, even if it's just representing physical models in that climate? I think these are very interesting questions. And maybe we can build enough trust looking into those climate regimes basically with a machine learning model. And you're right, in the sense that if you take any odd physical machine climate model and you run it you push it out of the comfort zone, it will for sure crash. I mean, it will not really kind of be able to kind of fulfill the test in the first go. I have never seen this. So yes, it is something to look into.
Then at this point, Peter, on behalf of LEAP, a huge thank you for joining us and taking the time to present this lecture. And for everyone in the audience or who will be watching this recording, please know that next Thursday, we will return to regularly scheduled hybrid programming with the lecture presented both in person at the Hub and via Zoom. So we look forward to seeing you in the future. Peter, thank you again so much. And we hope we'll see you soon.
Thank you for having me. It was a pleasure.